Chapter 13, Nuclear Magnetic Resonance, NMR. This tool, it's a very strong one when it comes to figuring out the structure of a chemical formula. So when I have IR spectrum, I can tell what functional group there are in that compound, on that chemical formula that I'm asked to predict its structure. But if I'm given the proton NMR or the carbon-13, I'm gonna get closer to what the structure in terms of connectivity is. This tool relies on atoms that have basically, that you see here, hydrogen, proton has 1, carbon has 13, nitrogen has 15, fluorine has 19, and phosphorus has 31. So they all share one thing in common, that is odd number of electrons. When the atom has odd number of electrons, it gives it the ability to do nuclear spin. This nuclear spin is the reason behind this entire spectroscopy tool. So the chapter does discuss proton and carbon-13, but you will be most responsible on figuring out proton NMR spectroscopy. Most of the time, the questions will be giving you a proton NMR, giving you a IR, and giving you a chemical formula, and asking you to figure out the chemical structure based on that. So when an atom does have a nuclear spin, this spin can be in the same line of an outside magnetic field or an external magnetic field, or opposite to that direction. So the one that's going to go with the same side of the external magnetic field or the same direction is going to be what they call alpha spin, and the beta spin will be when it's against the direction of the external magnetic field. The difference between the two energy will always be basically the one that we're going to generate peaks in an NMR spectrum. So what you see on the NMR spectrum is basically a bunch of peaks. They will be the result of having the nuclear spin, alpha and beta subtraction. That energy will be reflected on those peaks. This compound, if I take it as an example, I have CH3OH. So I have different hydrogens, the fact that they are connected to different atoms. The hydrogens that are attached to a carbon, they're going to behave different. They're going to spin different than the hydrogen that's attached to an oxygen. So the presence of an electronegative atom, usually it does actually cause what we call de-shielding effect. So it's very important to keep this term in mind. Why? Because it's when you look at an NMR spectrum, there are two regions. One is called upfield and one is called downfield. The NMR spectrum usually goes from 0 ppm, parts per million, all the way to 12 or 14 parts per million. The area that has a 0 ppm, usually we refer to it as the upfield, the shielded area. The hydrogens that show up on the closer to the 0 ppm usually are surrounded by less electronegative atoms, if any. The hydrogens that show up on their peaks on the left-hand side of the spectrum, which is called the downfield area, those hydrogens are surrounded by electronegative atoms. You could see here the example that we just referred to. CH3, for example, CH3 here will show up around, as we see here, it shows up around 3 ppm, while the OH shows up around 3.5 ppm. So the conclusion out of this slide that we always have to refer to the right-hand side of the spectrum being the upfield area, while the left-hand side of the spectrum being the downfield area. This peak low right here, we usually refer to it as the TMS peak. What does TMS stand for? Tetramethylsilane. Every single NMR spectrum, we want to make sure that we get the noise eliminated. What is that supposed to mean? I could produce an NMR spectrum, and that NMR spectrum may have a percent error, plus or minus some value. To make sure that that's not the case for any NMR spectrum that we generate out of a machine, out of an NMR machine, we insert a reference in the solvent. The reference is usually TMS, tetramethylsilane. We know already that the hydrogens on those methyl groups on the tetramethylsilane usually show up at 0 ppm. So if I have a sample and I run an NMR spectrum, proton NMR spectrum, and I see the TMS peak is at minus 0.5, what is that supposed to mean? That means all my peaks need to be corrected by plus 0.5. That's what it means. The chemical shift, which I just referred to as ppm, usually is calculated by the machine, but it's important for us to understand how it is calculated. Now, in the IR, we already learned that usually the values which are referred to as wave numbers are measured in reciprocal centimeter, while in NMR, usually that's referred to as chemical shift, and it's measured in parts per million, ppm. How is it usually calculated? It's usually calculated as the following: shift downfield from TMS in hertz divided by the total spectrometer frequency in megahertz. So if I see an example where the machine is 300 megahertz and the proton is absorbing at frequency of 2130 hertz, what do I do to figure out the chemical shift? I divide basically the shift downfield from the TMS point, which is 2130 hertz, divided by 300 megahertz, which is the power of the machine or the frequency of the machine. And that will give me the value in ppm, parts per million. This is very important to keep in mind, even though the machine does it for us, but we have to understand how it's usually done. This is the de-shielding effect that I was referring to earlier. So when you have, as an example, you have CH3 attached to an X that's an electronegative atom, such as fluorine, oxygen, Cl, Br, or I. We just seen the methyl sitting on the TMS is absorbing at around 0 ppm, and that's where usually the methyl hydrogens show up in that area from 0 to 1 ppm. So if you have, for example, ethane or methane or any alkane, you will always see those CH3 or CH2 or CH, they show up in that region of 0 to 1 ppm, sometimes a little higher to 1.5 ppm if it's a tertiary carbon, meaning you have a CH attached to 3 other carbons. But if you have a CH2 attached to 2 carbons, you will see it in a more upfield, meaning that you have less than 1.5. And the one that's going to show up the very first would be the primary carbon when you have a CH3 attached to another carbon. So what if the attachment was to an electronegative atom, such as fluorine, oxygen, Cl, Br, or I? The more electronegative the atom, the more the hydrogen is going to absorb in terms of frequency. Therefore, the chemical shift will be more toward more downfield. So you could see here that when you have the CH3 attached to an iodine, it's gonna the hydrogen is gonna actually show up at 2.2. If that's delta, that's basically the unit that we usually or the function that we usually measure the NMR with. The unit's still ppm, but the function is delta. So when it comes to having a BR instead, it will be 2.7 all the way to fluorine, which is the most electronegative atom among all these. You could see it's reading around 4.3. So the effect is called de-shielding effect. And the de-shielding effect usually is because of the electronegativity of the atom that's attached to that side of the molecule. So you could see it also clearly here, where if I have a methane, we'll measure the hydrogen will show up around 0.2 ppm. But if I have 1 Cl attached to the molecule, then I will have a 3 ppm reading, versus 2 chlorine attached, you will read it at 5.3. For the chloroform case, you will see it reading at 7.2. Most of the time we use chloroform as a solvent along with the TMS as a reference. So if I run an NMR sample using chloroform with TMS in it, I would expect to see the peaks that belong to the molecule and 7.2 ppm for peak for the chloroform and the 0 ppm peak for the TMS. So this is important. When I'm giving you a spectrum and you see a peak at 0 ppm, don't look for part in the molecule that's going to read at 0 ppm. That is the TMS. That's just used as a reference. If you see a peak at 7.2, most likely that's the chloroform. That's the solvent that's being used. Here's more examples. So you can see the alkane, all the hydrogens getting affected by having an electronegative atom, shifting from 0.9 to 3.4, the fact that you have a deshielding effect coming from the bromine atom. The further apart that hydrogen, obviously, the less it will be affected. You could see here when it gets to the gamma or delta carbon, away from that carbon that's attached to the halide, you will see it actually impacted the least. So this is a bunch of values that we're going to actually see our structures that we're going to be seeing their proton NMR spectra. This table serves as basically a reference for why these groups of hydrogens show up around that area. And you need to keep in mind that the deshielding versus shielding is what's going to affect the hydrogen to show up in an area versus the other. So let me just take an example. If I have a methyl attached to another carbon that has nothing on it other than just a bunch of hydrogens, then you're going to see it reading around 0.9. Look at the difference. If I would have this methyl attached to a carbonyl, look at the shift. It's 2.1. So it took it 1 ppm due to the deshielding effect that's caused by the electronegative atom, which is oxygen in this case. So you will see that also the case when you have a phenyl group attached to that methyl. It's about 2.3 ppm. So I could build up a trend based on this, that every single time I see a peak around 2 ppm, it's one of the two, a methyl or an alkyl group attached to a carbonyl or an alkyl group attached to a phenyl. So it's one of the two, and that will also depend on what other pieces of the puzzle that I'm given in the question that I should actually use to figure out which one is which. You can see here is another example where if I have an alkene, so here's an alkene H, it usually show up around 5 to 6 ppm. While if I have an alkyne H, it shows up around 2.5 ppm. So if I am in between alkene versus alkyne, and I'm asked, okay, match the chemical structure with the corresponding proton NMR spectrum, and I'm confused, is it an alkene or is it an alkyne? Well, I already know that the alkene hydrogen is the one that shows up around 5 to 6, not the alkyne H. Okay. So once again, it will be useless to just look at the table and try to memorize it. What you are advised to do, look at a lot of examples. You're going to build up trends, and the fact that you're going to see a certain moiety around a certain area every single time, that's going to make you remember. If you see it in a certain spectrum, you will know right away what that moiety or what that peak corresponds to, and so on. So let's start taking examples. So if I have this compound, I have basically acetic acid. So this is a proton NMR spectrum. That means I'm going to be looking at different things that have to do with hydrogens. These things that I'm going to be actually summarizing, they're all listed on one of the slides right here, which is slide number 14. NMR signals. What do we get out of the NMR spectrum? We get several factors. One, number of signals usually tells me how many different hydrogens I have. Not how many hydrogens, how many different hydrogens I have. Meaning, if I have 3 peaks on the proton NMR spectrum, that means I have 3 different types of hydrogens. 2, location. The location of the signal will tell me, is the hydrogen being deshielded or being shielded? That's another thing we extract out of a proton NMR spectrum. The third, intensity of the signal. What is that supposed to mean? If I see a peak and another peak next to it, that's 3 times the height of the very first one or the other. What does that tell me? That tells me I have 3 times the number of hydrogens of the first one. So that means I need to take that in consideration. How many hydrogens sharing that peak? That will be the intensity of the signal. The fourth, the shape of the signal, which is called signal splitting. This is an interesting outcome that we need to actually study really carefully. So I'm going to be visiting this point later on. But in brief, the shape of the signal or the signal splitting will depend on adjacent carbon hydrogens. How many hydrogens you have on the adjacent carbons? Plus 1. That's the rule that's called N plus 1. Once again, the signal splitting, it relies on the rule N plus 1, where N is the number of non-equivalent hydrogens on adjacent carbons. And I'm going to say this once again, once I get to the signal splitting details. So these are the 4 things that we usually extract out of any NMR spectrum, whether it's proton, carbon, or other spectrum types. But most of the time, you're going to see me talking about proton NMR spectrum in here. So let's go back to that acetic acid. So we're going to notice that we have a hydrogen attached to an oxygen and a hydrogen attached to carbon. So I have 2 different types of hydrogens. Therefore, I should be finding 2 different peaks. Here's a peak that's around 2 ppm, and here's another peak that usually shows up around 2 ppm. You could see it, it's actually, it's hidden. So that hydrogen right there, which is going to have another peak different from the CH3. But you could see here that it's 2 ppm. So that's an indicator of a methyl or an alkyl group that's attached to a carbonyl. And that's the case. What's that peak around 0 ppm? That's the TMS peak. Let's look at another molecule. I have CH3s. That's a terburyl group. Those CH3s, they are surrounded by the same environment. So they should be reading the same peak. Different from the methyl that's attached on the other side of the oxygen. Now be careful. When you say attached on oxygen, automatically those hydrogens on this carbon will be more deshielded than the hydrogen attached to those methyls, to those carbons. Why? Because the deshielding effect usually is caused by an electronegative atom. Those hydrogens are getting farther apart from the electronegative atom, so they're not going to be affected by that deshielding effect. So this methyl is expected to be around 3 ppm. So every single alkyl that's attached to an oxygen or an electronegative atom usually shows up around 3 ppm. But if you have a methyl that's attached to another carbon that doesn't have any electronegative atom attached to it, then you would expect it to be basically reading around 1 ppm or less. So the terburyl, here's a trend. Terburyl protons usually show up around 1 ppm. 1 ppm. And what we mentioned in regard to intensity, you could see here that the height of the peak is 3 times the height of the second peak. So that tells me I have 3-to-1 ratio. And that's true in this case. I have 9-to-3. So that's an important thing to keep in mind. So once again, 4 things you're going to extract out of any NMR spectrum, especially if it's a proton NMR. Number of peaks, different types of hydrogens. Location, shielded versus deshielded. In this case, methyl will be deshielded. Terburyl methyls will be shielded. The third, intensity. The intensity tells me basically how many hydrogens sharing that peak. And the fourth, signal splitting. What is that supposed to mean in this case? These peaks are singlets. Why is that? Because the rule that you need to figure out using that rule to figure out signal splitting is N plus 1. N is number of non-equivalent hydrogens on adjacent carbons. If I want to figure out the signal splitting for this methyl, I'm going to look at the adjacent atom. The adjacent atom is oxygen, has no hydrogen. That means my N is 0 plus 1. That's a singlet. The other one is the same thing. I have methyl, methyl, methyl. They're all going to share the same peak because they are surrounded by the same environment. Regardless which one you look at, you're going to look at the carbon adjacent to it has 0 hydrogens, so N plus 1 is 1. So that's a singlet as well. It's very important that you be aware of the table that is on slide number 40. It's telling you here the expected signal splitting. So if I have 0 hydrogens, I would expect the signal splitting to be 1, which is singlet. If I have 1 adjacent, that means 1 plus 1, that's 2, will be named doublet. This column tells me how I draw it. And we will look at those spectra coming up, and we will basically be able to see how usually we see a singlet versus doublet versus triplet versus quartet, and so on. If I have 4 hydrogens on adjacent carbons, and once again, let me make sure that I say this, non-equivalent, meaning I have hydrogens that are basically different from the hydrogen that I'm trying to find out the signal splitting for it. So if I have 4 plus 1, that would be 5. That will be referred to as quintet. 5 plus 1, that will be sextet. 6 plus 1, that will be septet, and so on. So this is important to be familiar with at one point. Most of the time, it becomes important how I draw the peak if I'm asked to draw to predict an NMR spectrum for a certain structure. But I will be lenient in regard to drawing the signal splitting. Most of the time, I will be asking you to match the structure or predict what is the structure that's going to be for the corresponding spectrum. So I'm not going to be, most of the time, I don't think I'm going to be asking you to draw an NMR spectrum. So let's go back to more examples. So if I have this structure, what do I have? I have a methyl ketone and another group that's an ester. So you could see here that this group and this group both are deshielding causing effect, both. But this CH2 is going to be the most in terms of deshielding. Why? Because it's being deshielded double effect. You could see that these hydrogens that are labeled C, they are surrounded by 2 deshielding effect, 2 carbonyl, more than the hydrogen that are sitting on the methyl. So the methyl, as you probably expected, is going to read around 2 ppm, while this CH2 is going to read around 3.5 ppm. So there should be a difference between the 2 types of hydrogen, the C type and the B type. While A is just another terburyl, and this time we're going to see it around 1 ppm. So different types of hydrogens, that's why we see 3 different signals. The second, location of the signal, it has to do with the deshielding versus shielding effect. Third, the intensity. We have 9 hydrogens sharing this peak versus 3 versus 2. So the height of the peak, it should actually be considered when I look at the peak and figure out which part of the molecule does really own that peak. And the last thing, which is the signal splitting, the shape of the peak. This methyl, the peak for it will depend on the adjacent carbon, has 0 hydrogens, so N plus 1 will be 1. So that's why it's a singlet. Same thing for these 2 hydrogens. They have 0 adjacent carbon hydrogens, so that's why N plus 1 would be 1. And the last thing, which is the terburyl, the same thing. So that's why you see a bunch of singlets in this molecule. Let's look at more examples. So if I have this, for instance, I have the trihalide. So I have a structure where there is a CH and a CH2. Apparently, these 2 carbons are surrounded different by 2 different types of environments. So the first one is surrounded by 2 halogen, 2 halides, and the second one is surrounded by only 1. So if I would be expecting how many different types of hydrogen, I would say 2 types. Why? Because I have a CH different than the other, which is CH2. That's one. Number 2, location. The location will be also affected by the deshielding effect. Having 1 halide, it's not going to be the same as having 2 halides. So right away, I would expect the one that's going to show up around 5.5 or 5.7 will be definitely the CH because of the 2 halides, the 2 Br groups. And the one that's showing up around 4.1 will definitely be the CH2 hydrogens. Okay, so that's the location. The third, the intensity. The intensity should also be an indicator to be used. So I have the height of the CH2 peak double the height of the CH. And the last thing is the signal splitting. The signal splitting of the hydrogen that's HA will be N plus 1, where N is the 2 hydrogens on the adjacent carbon, plus 1 that will be a triplet. The triplet is usually drawn in a way that's 1 to 2 to 1. 1 to 2 to 1. So that's how we draw a triplet. The doublet, why is it a doublet? Because HB has one adjacent hydrogen plus one, that will be 2. So once again, signal splitting, to figure it out, you need to remember the rule n plus 1. N, number of hydrogens on adjacent carbons. And once you come up with that outcome, it could be 1, that's a singlet, could be 2, that's a doublet, could be 3, that's a triplet, could be 4, that's a quartet, could be 5, that would be basically the outcome for a quintet, sextet, then septet. Anything beyond septet, you are free to use the word multiplet, multiplet. Okay, so once again, this is the table that you need to make sure that you be familiar with when you practice spectra, whether in your chapter or using the OER textbook or looking at the homework questions. You are free to use this table to answer these questions, but you need to be familiar with it before the time of the quiz or the exam, as this will not be given to you within an exam or a quiz time. Let's take more examples. What do I have here? I have a structure that's ethyl benzene. If I look at the structure, I should be able to figure out how many peaks I would predict on the NMR spectrum, the proton NMR spectrum. So first of all, this peak right here, that's around 0 ppm, that's the TMS. So that's out of the picture. That has nothing to do with the molecule. All right, what do I have now? I have a methyl, I have a CH2, and I have hydrogens on the benzene ring. Now the benzene ring, all the hydrogens that attach to a benzene ring usually show up around 7 ppm or higher. So that area between 7 and 8, always those peaks that show up around that region usually belong to an aromatic hydrogen. Don't get confused. The alkene hydrogen show up between 5 and 6. The hydrogens that are on the benzene ring will show up around 7 ppm or higher. Just keep that in mind. Okay, so if I have a CH2 that's attached to a benzene versus a CH3, I can tell right away the CH2, because of the inductive effect or because of the deshielding effect coming from the benzene, I wouldn't expect the CH2 to be more upfield. It will be actually more downfield. So you could see here that the area to the left, it's more downfield than the area to the right, which is upfield. Keep that in mind. You could link it this way. Deshielding happens, taking it more downfield. Shielding happens, makes it go upfield, and so on. Okay, upfield goes toward the 0, downfield goes towards the higher ppm values. Okay, so that's one. Figuring out that CH2 is going to be more downfield than CH3. The second, CH3 is going to read a triplet, and that's what you have here. While this CH2 is going to have 3 plus 0. That's 4, that's 3 hydrogens, plus 1, that will be a quartet. The quartet shape, it's usually drawn in a way that's 1 to 3 to 3 to 1. And you will probably see it here already. So the peak will be drawn in a way that's 1 to 3 to 3 to 1. So that will be an indicator of a signal splitting of quartet. Okay. Now, am I responsible to figure out within the 7 ppm where these hydrogens are? Well, in that case, no. When it's a mono-substituted benzene or di-substituted structure other than para-substitution, meaning you have a substituent on this side and another substituent on the other side that's opposite to it, you're not going to see in this course. So you're not going to be dealing with other than mono-substituted benzene or di-substituted benzene that are para to each other, meaning 1,4 di-substitution, 1,4 di-substitution. So all the examples that you're going to see in the homework or quiz or in the chapter, they're going to be actually what you're going to be seeing similar to them in the exams. Okay, here's more examples. So you have the CH3, carbonyl, CH3, CH3. You could tell right away that I have 1, 2, 3 peaks. Why these two methyls are the same peak? Because they are surrounded by the same environment. Okay, now these two methyl, they're not going to be the same in terms of location to the other methyl. Why? Because this methyl is attached to a deshielding causing effect, that's carbonyl, versus these two methyl are surrounded by a CH. So this methyl will read around 2 ppm, while these two methyls, they're going to read around 1 ppm. That's the difference between the two because of the deshielding effect. Now this CH, obviously this CH will be next to a carbonyl. Now this will also be reading around 2 ppm, but I have A and C. Which one is going to read more downfield? The one that's more substituted is going to read more downfield. And I already mentioned this previously. If I have a CH3 versus CH2 versus CH, where do they usually show up? The CH3 would show up around 1 ppm. CH2 would show up around 1.2 ppm. The CH will show up around 1.5 ppm. So the more substituted the carbon, the more deshielded its hydrogen. So just keep that in mind. Okay, so that eliminates the number of peaks and eliminates the location. Now, let's talk about the intensity. I have 6 to 3 to 1, and I should be able to see that. So I have basically this been clearly has been cut. So this should be 6 to 3 to 1. So that tells me how many hydrogens shading that peak. Last, which is the signal splitting. What do I have? I have a singlet because I have 0 adjacent hydrogen, and that's what I see here. I have methyl and a methyl surrounded by 1 hydrogen. So these two will read a doublet because they have 1 adjacent hydrogen. And that's what we see here. It's a doublet. And the last one, which is C, surrounded by 6 hydrogens, plus 1, that's 7. What is that? That's a septet. That's a septet. If you count those, you will have 1, 2, 3, 4, 5, 6, 7. So that's a septet. So it's important for us to, when we match a spectrum with a corresponding structure, we want to make sure that those pieces, they add up. The location, the intensity, the signal splitting, and obviously the different types of hydrogens that we should have in the molecule because of those peaks that's showing up. Okay, more examples. So we could have better understanding. So here's another structure. What do I have here? I have the 1,4 disubstituted benzene. And I just mentioned, you will be dealing with monosubstituted benzene or 1,4 disubstituted benzene. You're not going to be seeing anything else other than those when it comes to proton NMR spectrum. All right. So what do I have here? I have a methyl. I have hydrogen attached to the aromatic. So I'm going to be looking at 1 peak for the methyl, 1 peak for this hydrogen, which is similar to the HA hydrogen, and 1 peak for the HB that's similar to the other HB. So there is equivalency when it comes to hydrogens on the ring when it's 1,4 disubstituted. Why there is equivalency? Because once again, this HA is surrounded by an environment similar to the other HA. HB is surrounded by an environment similar to the other HB. So it makes sense that they will read the same peak. Okay. Where would the methyl read? Will read around 2 ppm, and that's what you see here. How about the hydrogens on the aromatic? They will read in 7 to 8 ppm. And those hydrogens, how are they going to read? Well, HA is going to have 1 adjacent hydrogen plus 1 that will be doublet. And the other hydrogen will do the same. We'll read 1 adjacent hydrogen plus 1, that's a doublet. So I'm going to be reading every single time I have 1,4 disubstituted structure where those two substituents are different, I would expect to see doublet and doublet in the 7 to 8 ppm. And that's what you see here. Let me repeat what I just said. That's another trend that you need to add it to your list. If I have 1,4 disubstituted benzene and those two substituents are different, I would expect to see doublet and doublet in the 7 to 8 ppm. So now the next question would be, okay, which one is which? Well, this doublet that's going to be more deshielded is going to be HB due to the fact that you have a deshielding effect, which is the nitro group. Methyl is not a deshielding effect. Methyl is a shielding effect group. So that methyl is going to make the hydrogen more upfield. So that's the difference between the two. That HB would be the one that's around 8 ppm, while HA will be around the one that's going to be around 7.3 ppm. Here's some more examples where you would see basically an alkene hydrogen, and you have the two methyl groups, and you have the CH2s. Okay, so one hydrogen on that side of the alkene that's different than the other. How could it be different? Well, this hydrogen is closer to a carbonyl. This hydrogen is closer to an alkyl group. So you wouldn't expect these two hydrogens to be reading the same. So that's why you see two different peaks, one around 5.9 ppm, which is most likely the one that's down here, and one reads around 6.7 ppm, which is the one that's closer to the carbonyl. So the deshielding effect will cause it to be more downfield. Okay, though the hydrogen that's on the carbon that's adjacent to a carbonyl, that will be the one most likely around 2.5 ppm, and the hydrogen that's farther apart will be around 2 ppm. And finally, the two methyl groups will be the one that's around 1 ppm, the fact that they are not surrounded by any deshielding effect. All right, so that's the location, and that's the number of peaks that I would expect. Let's talk about intensity, which is the thing. Let's talk about intensity. So we have 6 hydrogens sharing this peak. We have 2 and 2, and we have 1 and 1. So that's how we will basically figure out the integration or the intensity. How many hydrogens sharing those peaks? Okay. The final thing to extract out of this proton NMR spectrum is the signal splitting. So the shape of the peak. Why is this singlet? Because these two methyl groups have 0 adjacent hydrogen. +1, that's 1. That's why it's a singlet. Okay. Next would be the CH2 right here. Has 2 hydrogens attached on the adjacent carbon. So that's why 2 + 1, that's 3. That's why you see it's a triplet. Same applies to the other carbon. So the other carbon is going to read the one underneath. It's going to have 2 hydrogens, so +1, which is the N+1 rule. That's why it's a triplet as well. Okay. How about the alkene? Each hydrogen is going to read the other. So that's why you're going to see a doublet and a doublet. A doublet and a doublet. Okay. Coupling constant. That's another thing that I would consider if I am debating whether I'm dealing with a cis alkene or a trans alkene. Cis alkene or a trans alkene. So the coupling constant is not a thing that you're going to be asked to calculate, but it's important to keep in mind what it is and what it is about. So coupling constant is a factor that we use to figure out whether we have a doublet of a cis or a doublet of a trans. So how wide the doublet is, it's more indicative of a trans. How narrow the doublet is, that's more indicative of a cis alkene. So if I have a trans, I will have much higher coupling constant, which is around 15 to 20. But if I have a cis, I would be reading it 10 or less hertz. So this coupling constant sometimes is really useful in a case like this one, styrene. What do I have? I have the aromatic hydrogens, and I have a hydrogen on the alpha carbon to the benzene, and I have 2 hydrogens on that other side of the vinyl group. Okay, so how many peaks would I expect other than the aromatic peaks? So I already know that the aromatic hydrogen will show up around 7 ppm. So let's put those out of the picture, and let's just talk about the other ones. So if I look at the structure, I would expect 1 peak for HA, and I would expect 1 peak for the CH2, based on what I learned previously. But because of the coupling constant, that it does play a role in figuring out whether that hydrogen is surrounded by a cis hydrogen or surrounded by a trans hydrogen, I will see different peaks for those 2 hydrogens, even though they are on the same carbon. What I'm trying to say here, that you will see a peak for HA, you will see a peak for HC different than the peak for HB. How come? HA will be affected by, once again, the 2 hydrogens together, meaning HA will read HC different than reading HB. That's why you see a doublet and a doublet. So those 2 doublets, they belong to 1 hydrogen, because that hydrogen, which is HA, is not going to read HC the way how it's going to read HB. So once it reads HC, it's going to apply the rule N+1, so that's a doublet. Once it reads HB, N+1, that's again, that's 2. That's why it's another doublet. So that's why you see doublet and doublet. They are right next to each other, belongs to the same hydrogen. Okay, how about HC? HC is going to look at the adjacent carbon, is going to have 1 hydrogen +1, so that's a doublet. B is going to look at the hydrogen on the carbon adjacent to it, so that's going to have also another doublet. So I have 2 doublets for those 2 hydrogens. So 1 doublet for HC and 1 doublet for HB. But which one is which? Well, the HC is cis to HA, while HB is trans to HA. I would expect that to reflect on the peak, even though it's almost surrounded by the same environment. So you could look at the 2 peaks and look closer. What do I have? I have a narrower doublet versus a wider doublet. The wider doublet reflects the trans, the narrower one reflects the cis. So right away you could tell that HC is the one that's around 5.15, and HB would be the one that's around 5.69 or 5.7 ppm. So this is really important to keep in mind. So J coupling, once again, it's a factor that we use to figure out whether I'm dealing with a cis or trans alkene. And those hydrogens that usually are cis, they would have a J coupling of around 10 hertz. So the doublet will be a narrow one, versus the trans one, which is going to read around 15 or higher hertz J coupling value, that will be having a wider doublet. Okay. OH also is something that we could consider to have its own peak, but because of the hydrogen bonding, OH may have a wide range where it will show up. It might show up around 1.5, might show up around 2, might show up around 3.5. So there is no really a set region or location for the OH, and the same applies on the NH. So those hydrogens of an OH or an NH, if I'm asked to figure out which peak is which for which part of the molecule, I would leave the OH and the NH until the end. It's very important to mention the following. Every single time you deal with an alcohol or an amine, the hydrogen on the oxygen, regardless what adjacent carbon hydrogens there are, hydrogen will not be reading those hydrogens. The hydrogen and the oxygen will not be reading the 2 hydrogens on the adjacent carbon. So the de-shielding effect that's caused by the oxygen is going to prevent the hydrogen attached to it to be able to read the hydrogens on the adjacent carbon. So when I apply N+1, N will be 0. +1, that will be a singlet. So this is important to keep in mind. So if I have ethanol, I would expect the CH3 to have its own peak, CH2 will have its own peak, OH will have another peak. So 3 different peaks. Next, I would expect the CH3 will be the most upfield. CH2 will be more downfield compared to CH3. And now OH. Now the CH3 will be a triplet, while the CH2 will be a quartet. And you could see it clearly here. The CH3, which is around 1 ppm, it's a triplet. The CH2, which is a quartet, it's around 3.5 ppm or 3.7 ppm. And the last thing, which is a triplet or the singlet of the hydrogen that's attached to the oxygen. All right, carbon-13 NMR. It's another tool that we use to confirm connectivity of a molecule. What is that supposed to mean? Most of the time, we're going to rely on proton NMR spectrum to figure out how the structure is connected. Next, what we're going to be using the carbon-13, if needed, to confirm a molecule. And I'm going to rely on one method that's really useful when it comes to carbon-13 NMR. So first, let's start with this, knowing where usually the groups are. Now, if the proton NMR spectrum goes from 0 to 14 ppm, the carbon-13 NMR usually goes beyond 14. So it goes from 0 all the way to 200. The one that usually shows up around 200 ppm is the carbonyl carbon. So every single time I'm given a carbon-13 NMR and I see a peak around 200 ppm or close to it, like 180 maybe, then I most likely have a carbonyl group in the structure. It could be a carbonyl, a ketone, aldehyde, ester, amide, any of those. So that's important to keep in mind. Next, you will have the aromatic or the alkene, which is around 100 to 120. Next, around 7 ppm, where the carbons attach to an electronegative atom. And finally, the alkanes, which are usually 30 and less ppm. So if I have two peaks, one around 30 and one around 70, I know for a fact that the more deshielded the carbon peak, the more basically downfield. That's important to keep in mind. So deshielding, shielding also affects the carbon-13 NMR. The reference, which is the peak that's going to show up at 0 ppm in the carbon-13, that's also referring to the TMS. So don't forget that. So here is the tool that I want you actually to pay attention to. Carbon-13 usually will just show up a bunch of peaks and all of them are singlets. So if I take this, for example, as a compound that I want to look at, it's carbon-13. What am I going to see? I'm going to see 1, 2, 3 different peaks, but all of them are singlets. So if I were to know which one is being more deshielded than the other, I wouldn't know which peak is which. But here's another method that's more useful. It's called off-resonance decoupling carbon-13 NMR. Off-resonance decoupling carbon-13 NMR, it gives you signal splitting of every single peak in the carbon-13 NMR. What is that supposed to mean? Look at this molecule, the one that we just saw, that has a bunch of singlets. What do I have here? I have CH3. I have 3 hydrogens attached to that carbon. Therefore, N+1 would be quartet. And that's what I see here. Wait a minute. You just told me proton NMR, N+1, where N is the adjacent carbon hydrogens. Yes, it's different when it comes to carbon-13. Carbon-13, you count the hydrogens attached to that carbon to figure out the signal splitting of that carbon. So the signal splitting of the CH3 would be 3+1 quartet. The signal splitting of the CCl2, no hydrogens at all, so that would be a singlet. The signal splitting for the CH2 would be a triplet because I have 2 + 1. That's why you see it's a triplet. So this method is much more actually useful than having the regular carbon-13 NMR method. So the off-resonance decoupling carbon-13 is a very useful tool that we should actually rely on to not just confirm connectivity. It might actually be helpful to build up a connectivity based on it alone. And you could see the TMS is showing up around 0 ppm. Why it's a quartet? Because of the fact that you have 3 hydrogens attached to that carbon, so that's why N+1 would be a quartet. And here's some more examples, so you could see the difference between the off-resonance and the regular method. So the regular method will expect to have 1, 2, 3, 4 peaks. The one further around 200 ppm, that's the carbonyl. This method versus this CH2 would be next to each other. And the very first carbon, the CH3, will be the one that most upfield. All right. But if I look at the off-resonance, I could see clearly I have quartet and a quartet. So I could tell right away which one is which. That this peak is the CH3 and this peak is the CH2. So that's really easy to figure out connectivity of a molecule relying on the off-resonance decoupling method. And today, this method is being used in what we call MRI, but because of the fact that it's scary to say nuclear magnetic resonance imaging, we took that nuclear word off and we now use a more attractive term, that's MRI imaging. So magnetic resonance imaging. So that makes it less scary, but it does use actually the same strategy, how to figure out what's within those cells once we scan them. And that's chapter 13.